today we'll start with the elements from science basic. And we will take a very quick review of the quantum mechanics. I expect you should know. But it's just a starter. Then the important point is one is to find the solution with the finite quantum wave. Yeah, surely probably you learned the solution of the quantum wave or infinite quantum wave or finite quantum wave in some way. But today we're going to do a little bit deeper. Yeah, while including trying to find the numerical values with real materials. Yeah, and then we will also give a quick review of the band structures of the semiconductors. But the point is not the band structure itself, because I will also assume you should have some basic knowledge about the band structure of the semiconductor. What's equally important is that we also need to calculate the carrier densities with actual semiconductors, since we are not going to still stay at the level of theories. Okay, so in quantum mechanics that we learned, wave and the particle actually are not two different things. In a scale of nanometers, waves can be treated like particle, and the particle can be treated like wave. So in classical mechanics, we differ the electron and the light with different formulation. Like for electrons in classical method, we treat it as a particle. So a particle has a specific position. Yeah, you can describe it as a point. Yeah, and but in the order of quantum limits, we have these wavelengths. Because the wavelength is something in a way, and the relation is bridged by something called the Broglie relation. That the wavelength is inversely proportional to its momentum. P is equal to h bar over lambda. So in the normal level of P, the lambda is really small. So in the broad scope, you just cannot feel the lambda. Yeah, and the wavelength, the wave-like property of particle also brings us something called the uncertainty principle. Yeah, that's also the rule of thumb in the quantum mechanics. And this is just something with a pure statistic. It's a mathematical result, it's not a physical result. It's while you describing something in a continuous function, you must have a relation like this. But that's not what we are going to talk about today. And for the light, yeah, in the microscopic field, that we always write the light as a field, probably in the cosine or sine way. So it has its amplitude, its wave vector, and its frequency. And then we always said that the energy, the energy is proportional to the square of its amplitude. But in classical meaning, we think this is a continuous function. But if we also go to a very small scale with very few energies. The first is from Planck, and the second from Einstein, and so on and so on. We said that the energy increment has to be quantized. It needs to be some integer. Times is a fundamental energy, we call it photon, and then the energy is called h bar omega. So to illustrate, to describe the behavior of electron, we need to use a wave function, and the wave function stands for is the probability of existence. That means if you take its conjugate and the time itself, you get a square value, and the value will be representing the probability of finding a electron in a specific position. For example, if I find a wavelength in position, the wavelength is strongest in the middle. That means you are more likely to find the electron in the middle. And y is 0 at the side. That means you will never find the electron over there. So we can then go to another idea called boundary state. Since you are describing something with a continuous function. That means if this function doesn't the probability of doesn't goes to 1, that means you are going to find it everywhere. Yeah, because after normalization, you cannot find any wavelength at the specific point. So if a wavelength has a property that its conjugate times itself and the integrate all over the place is a finite value. At the beginning, you can see something probably not 1, but after normalization, it will definitely goes to 1. So if the wave function is bounded, that means you can do a integral, and the final integral is a certain value, not infinity. Then we call it a bounded state. So this is the first boundary condition while you're finding its wavelengths. The wavelength must be a bounded state or it doesn't exist. Second, if the wavelength, if something is described by a wave function, it must be continuous and differentiable. Why? Because since the wavelength stands for the existence, the probability of existence, so you cannot have 2 probability for a point for its existence. So it must be a continuous function. That means for a certain point, it's x plus and x minus. That means a little bit more than x or a little bit less than x. The value should be consistent, or it physically doesn't sound. Yeah. So it also maps to the conservation of mass. And simultaneously, because the derivative of wave function is relevant to its case, since you are describing its like an since you are describing its weight, so it will be something like an exponential I k x minus omega t. This is what we know as the wave function. So after you taking a position differential, you will omit ik out. Yeah. So taking a differential meaning finding its energy momentum. So if its differential is not continuous, that means its momentum is abruptly increased or abruptly decreased at some point. That also doesn't make sense because that will violate the conservation of momentum. So these two are mathematical relation for the wave function, and it corresponding to a physical relation in the quantum mechanics. So in general, we need to solve the wave function with the corresponding equation. Then make it suitable for all these boundary conditions. Then the final answer will not be will be discrete. There will be infinite combination of k and omega. Yeah, that's the something we call the state. So then, in order to find the physical property of the wave functions, usually we have expectation value and the operator. Since the existence of the particle is not specific, it might be here, it might be there. So the parameter will not be specific also. Because while electron is in somewhere, it might have a higher momentum. But while it's in the other place, it might have a lower momentum. So you can only average the possible momentum. So the trick is that you find a corresponding operator which will extract the property out of the wave function. In this case, because we know that the momentum is a function of k, then we can do a differential to extract the momentum out. Then to do with the average, the space average, then we have its expectation value. It's just like a weighted number of something. So to evaluate its expected or average position, we just type x. To evaluate its momentum, you need to take a differential. times IH bar. Because you have I, you need to times minus I to make it pure K. Yeah. So and the times H bar, because H bar K is your momentum. So because P is equal to HK. Yeah. So in order to get K, we need to times minus I to get only K, then times H. So the momentum is minus IH bar. Then you can extract something out. Potential still also is potential. If it's hydrogen, probably the potential is just the statistic of the minus q squared over 4 pi epsilon r. And for harmonic oscillator, that is the momentum now is a parabolic potential function. Yeah, and the simple case is for the infinite quantum wave. Alright, so in class mechanics, the rule of thumb is the total energy is equal to its kinetic energy times plus its potential energy. So in the quantum world, we have to take all the expectation. So it will be the expectation of energy equal to expectation of kinetic energy plus the expectation of its potential. Then the operator of momentum is is partial over partial t. The operator of the P is IH bar, so times double itself will be minus H bar squared times Laplace. And the potential in the okay, so this is something we know the time dependent Schrodinger equation. However, if the potential is stable, B is not a function of time, it can be further reduced to the Schrodinger equation like this. So this is the Schrodinger equation most of you will encounter, because actually very few people will actually solve the time dependent Schrodinger equation. So this is the form of is the Newton's second law, 牛顿第二定律 in the quantum world. So this equation is actually alright. So here is a summary. So how do we find the potential for the time independent? How do we find the wave function for time independent potential? First, you need to describe its potential property. Second, you put the potential into the differential equation here and try to solve it. Then you might have so many combinations. Yeah. But with so many combinations, you need to fulfill following stuff. First, when x it's going to minus plus infinity, it must go to 0. Or you cannot normalize them. Second, the phi is continuous everywhere. So usually we only need to find the position at a certain interface, because you usually solve the differential equation with continuous function. So the only point you don't need to check every point to be continuous. You only need to check the interface is continuous. And the third, its first derivative, 一次微分, is also continuous. So okay, so this is the most common case of the Schrodinger equation is the infinite quantum wave. Infinite quantum wave, that means with a certain length, we call the length to be L. So it will be minus L divided by 2. And to the plus L divided by 2. Then it's 0 at this region. So phi over r is 0 if x is the absolute value of L. Absolute value of x is less than L over 2. Second, if L is infinite. So when it's infinite, that means the electron cannot exist at that point. So we can just directly assume the electron outside the well, the probability is going to be 0. Okay, so outside the quantum well, the wave function is going to be 0. And inside the quantum well, because the V of R is 0 here, so this is just a simple Laplacian, and its solution should be a wave equation. So you can write down the phi of x should be either way of that. One is the a cosine kx, or b sine kx, or the combination of them. So because we need to go faster, we just tell you it's either a cosine x or b sine x. Then, if you put it down, you will see the relation between k and the e will be k squared is equal to 2ne over h bar squared. Alright, so you have a function here. Then, because the wave function needs to be continuous, so when phi of x is equal to half over L, a cosine KL over 2 will be 0. So the k will be pi over L times odd integer. If the case of sine a sine x, then the k need to be 2 pi L over L. That means L over pi times the even integer. So in the general case, the k will be pi over L times the arbitrary integer. Then E is equal to 2m h bar squared k squared. So you can just move it here and move it back. So you get something like this. And since you can pull the n out, so it will be n squared times the E1. E1 means the ground state. This case, the n is equal to 1. And infinity denotes the quantum well is infinitely deep. Alright, so the E1 will be h bar squared pi squared times 2ml. Yeah, because we just need to put the pi back to the relation here. You can write it out something like that. Alright, so since now we have a lot of constant here. Here the h bar is constant and the m is pi constant. L is something, but we can firstly put it a constant. Here, for example, we can let it assume 10 nanometer. Divide it by 10 nanometer and times by 10 nanometer. Then, divide it by the rest mass first. Then divide it by its n squared. So, the rest of them is already a constant. So, we can calculate it out. So, the answer is a constant equal to 3.76 MeV, milli-electron volt, times the reciprocal of the effective mass， 就是它的那个有效质量是多少去导数 ，OK， then times the 10 divided by is let the width of the quantum well. Okay, we will have some example later. Alright, so the finite quantum well case is really simple, but we need to directly go to, but the infinite quantum well is really simple, but now we need to directly go to the finite quantum well. So let's assume a symmetric quantum well. That means the VF of x is 0 while it's inside the well, but a certain value, not infinite, outside the quantum well. So in the region 2, inside the quantum well, V is 0. So the answer is still A cosine kx or B sine kx. Similarly, k squared is 2me divided by h bar squared. However, if in region 1 and 3, V is something called V0. So the Schrödinger equation becomes so it shifts to V0 here. However, in the V0 must be somewhere between 0 and V0, the E, because if it is not, you cannot have a bounded state. So we can already assume the E will be something between D and V0. So E divided by V0 is something negative. So the wave equation could be written in D exponential minus alpha times X divided by 2 over L. So it is just a smart way to write it down like that. Then alpha, the relation between alpha and the 0 will be alpha squared equal to 2AB over B0 divided subtract. Since we already assumed that the B0 should be larger than D. Alright. So after we write it down like that, we need to fulfill the boundary conditions. The first is phi is continuous at the L divided by 2. That opens the L the donation. So we just put it back. So for the symmetric case, A cosine KL divided by 2 should be D. Second, if it is a symmetric case, similar, B sine KL divided by 2 should be D. Okay, then when for the case of the differential, A cosine KL divided by 2 will be leave K out, so KA sine L KL divided by 2 should be alpha D. Similarly, you have KB cosine KL will be minus alpha D. Then you divide both sides. Alright, so you divided these two. So you have divided alpha at both sides and no D at both sides. So it will be tangent KL over 2 should be alpha divided by K. The other way will be minus cotangent KL over 2 should be alpha over K. And with some calculation, this is equal to tangent KL over divided by 2 minus pi over 2. Alright. So how do we solve this equation? Because this is something you cannot solve easily. This is a tangent of K, and this is a tangent. This is 1 minus the inverse of K. So you cannot solve it directly because this is something rather difficult. So we need to further do some trick, then do it with graphic. Alright, so recall that the relation of the alpha and K is something like this. So if we plot both sides, K squared plus alpha squared will be 2m B0. So that doesn't even matter where the E is, it must be right. So the K squared divided with plus alpha squared should be 2m B squared, so it should be a constant. So you now have a relation that the K and the alpha as a relation like this. And then we times x bar squared and divided by 2n. So this is the other expression of the boundary condition. Then so this is really a trick. In order to simplify the case, we need to borrow the energy here from the infinite quantum wave. If we divide it by both sides, we let your new energy is normalized to the E1 infinite. And the relation is NQW squared. So this becomes the value we want to know. If we can find NQW, and we notice what it is, so we know what the energy is. So this is the NQW is something we want to solve. Second, the V0 is also normalized to the infinite, the first the ground state, and the proportional constant is a max. That means the maximum energy it can be, because if your energy is larger than that, it cannot be a bound state. So this is also a value given. 这是边界条件，这不是要算的。 So if we have a V0 like this, we can divide it by the ground state in the infinite quantum world. Then this is the new parameter we have. Alright, so now we divide the E0 on both sides. We have the boundary condition becomes simpler. It becomes NQW squared plus alpha L squared divided by pi max squared. Then after some arrangement, so this is detailed arrangement. You can check with we can do that one by one. The final boundary condition becomes like this. It's a uniless number. First, the first one is tangent 2 pi divided by 2 times NQW. Is equal to 1 of NQW in 1 divided by NQW times the square root of N max squared minus NQ squared. Okay, so this is the symmetric case. And the symmetric case. And the asymmetric case is just a shift by half of pi. Alright. So it looks like this. So for the left hand side, LHS, it is the tangent and the tangent minus it's all tangent and the tangent with a shift of 1. So this is tangent. And the second one is the shift of tangent, is the cotangent case. Okay, so the left hand side is this curve. Alright. And what does the right hand side looks like? Because we are trying to solve what the NQW is. This is the value we would like to know. So that's a two extreme case. The first is if NQW approaching 0. We are talking about the right hand side of the equation. If it's approaching 0, then the Fortran goes to infinity. Okay? But if NQW increase, how much it can increase? It can increase go to a max. It's the boundary because the energy cannot be higher than V0. Then the right hand side becomes what? It becomes 0. So if you plot the right hand side with NQW, it will be a curve starting at infinite number, then ending with 0. Then when does the relation become satisfied? That means when the left hand side is equal to the right hand side. So those points is your solution. Although we cannot directly tell you what it is, but you can plot them and find it one by one. So as long as your max is not 0, it's something larger than 0, and that means you're still starting with at infinite. Then gradually it goes to something near a max, because while n is go equal to max, it will go to 0. So at the next, there will be one solution. As the n max increase, so you will start from here and go to much further. So the number of the n max will decide how many bound states there will be in the quantum world. Okay. So luckily, although this position cannot be done like with hand, but this textbook is very considerate. He provides you the numerical approximation about where the ground state is, aka where is the first intersection here. He already plotted like this. Okay, let me tell you how to read this figure. This is the max. Max represents how deep is your quantum well. And this is the corresponding NQW. If your max is 0.5, then your NQW is something here. You can try to do it by figures. Probably we don't know what it is. Okay. If n is larger than 1 and less than 2, you will find the 2 available states for your energy. Similarly, if n is larger than 2 and less than 3, there will be 3 states with corresponding NQW. Okay, so if you have the tool with a computer, you definitely can find that. You can just plot both sides first and enlarge the B figure, and you will get the point with a certain accuracy. But since this thing is developed probably 40 years ago or 50 years ago, by the time we don't have a good computer, so lots of people trying to do numerical approximations. That means they want to find an equation that if you put a max in, you can directly calculate the NQW. Although it's not specific, as long as it is close enough, that will be good. So this is this equation doesn't sound really basic, but this is very useful to evaluate the ground state energy of a finite quantum well. That means you will first calculate what the max is. Then put the max into this equation. That means you times max times 1 plus 0.6 powers 1 plus max. That's a funny one. You cannot even know what the basic. So this is not basic, it's just a numerical approach. Then do an arctangent on that. Then times 2 divided by pi. So this is roughly the symbol of roughly. Because this is a very good approximation, because this equation describes this real curve with less than 1% error. So this is proven. So in this case, as long as you have a quantum well, I give you a depth of the quantum well, you can directly calculate that. You don't really draw that from the bottom. So here's an example. For example, we have aluminum arsenide, gallium arsenide, aluminum arsenide quantum well, single quantum well. And the quantum well is 3 nanometer. And it is sandwiched by the bulk aluminum arsenide. For convenience, we just let the effective mass to be the same. Yeah, sure. If it's not the same, we still can find a solution, but we can no more use this equation. So for practical reason, I will always assume there will be the same thing. And in real cases, it also doesn't differ much, so it's okay. Then the band offset. The band offset means what's the delta EC divided by delta EG. Okay, delta, for example, it says that if the band offset delta EC over delta EG is 0.66. That means if the quantum well of the aluminum arsenide is 2.16 eV, then your band gap of gallium arsenide is only 1.42 eV. Then you have a delta EG, right? But the difference of a band gap will be distributed in conduction band and the valence band. So that will have a portion. So this is another material parameter called band offset between two materials. That means because you have a band gap of two materials, but you needed the additional number to know how many differences it goes to EC and how many goes to EG. So the answer is 0.66. And this is also a commonly used value. It's usually between 0.6 and 0.7. Although it doesn't differ much, but in calculation it makes a very big difference. So while we're doing simulation, we always need to try to change this value to fit the best result. But you cannot make it too unreasonable. For example, you can assume it to be 0.8. That will be unphysical because it doesn't go that far. It's usually a value between 0.6 and 0.7. Anyway, I will just tell you in this case, let's assume it's 0.66. Alright, so let's see what's the position of the ground state in this material. Alright, so we know that the band gap of aluminum arsenide is 2.12, and the band gap of gallium arsenide is 1.42. So delta EC is 0.66 times it, so that will be 0.488 EV. So let's write it in EV, that will be cleaner. So the delta EC is 488 millielectron volt. Second, because we need to normalize it with the ground state energy of infinite quantum well. So we have a relation here. So what's the ground state energy of the infinite quantum well? We just put a number in. So the m is equal to 0.007. So it's just putting the number in. And the quantum well is 3 nanometer. Okay. So if this is the infinite quantum well, the ground state should be 623 millielectron volt. Alright, so then we can normalize the depth of the quantum well now. Okay, so in this case, so we would put the 488 and the 623 in, and take a square root. Okay, that means the Nmax is only the 0.885 higher times of the infinite quantum well ground state energy. Alright, so you have the Nmax, you just put a number in. You have NQW. Then you have NQW, put it back. You have the solution. So this relation is important and useful. If we don't have a relation here, what we can do at the most is to derive this energy and tell you a result that the number of available states and the number of available and the relation to is well depth. With this approximation, that means that makes us some real calculation possible. Okay, so after calculation, we find that the ground state and the delta N is 198 MeV. Okay, so because in finite infinite quantum well, we already assume this is the 0. So then you calculate En1 is 198 MeV. That means this level is 198 millielectron volt above is easy. Then you have this ground state here. Similarly, you can also find the ground state if you have the correct effective mass of your host. Then you can find the Bose energy of such quantum well. Okay, that's the textual break.